sort of chosen as a location because it was as far away from everything as possible. So some of the biggest technological issues that we have are things like goannas eating the wires, nuisance. A lot of sun bleaching as well for the wires. And they did a sort of cost-benefit analysis and found instead of digging trenches for all of the wires to cover them from the sun and sort of save them from sun bleaching, it was actually just cheaper to let them be sun bleached than digging because there were just that many cables. So, sorry. That's it. Replace the cables over time. We're all good. Back online. Amazing. Oh, and now I've lost my laptop. Oh, goodness. All right. That's my tech issue. A delay. Oh, go to this one instead. Right, I see. Okay. Well, hopefully as I keep going, that shouldn't be an issue. Okay, so. Yes, I can restart. Sorry to everyone in the room, you have to listen to my introduction again. It's a really rough time for you all, I know. So, hi, my name is Kat Ross. And if you look on this slide, you will see that there is one very interesting word there, the proto-Dr. Kat Ross. We've had a very long discussion about that now in the room. But for those online, the proto is because I'm not quite yet a doctor. I've submitted my thesis and I'm waiting for it to be accepted. But a couple of days ago, I got my reviewer comments and they've recommended that I pass with only minor changes, which is very exciting. And thank you to both reviewers who read all 300 pages of that thesis. So moving on to just my background and general life history. So always was very interested in astronomy from a very young age. As we can see here, little baby cat, where I was very interested in astronomy and space, wanted to get out into space. As you can see here, this is not a very safely constructed outfit for space. And actually a fun little anecdote, it was around this age that my family used to frequently go out onto the street and watch as the International Space Station went overhead. And it was unbelievably exciting as a little kid, just seeing a moving dot and knowing that that was in space, this feat of engineering and science. It's just amazing to be able to see it. And then my parents told me that people live up there in that moving dot that's going overhead. And so little baby cat interpreted that as, well, if people live up there, they have to do their business up there. And so I don't want to get hit by flying space poop because of this. And so to this day, my family, every day, every time the space station goes overhead, we all cover our heads to block the falling space poop. So this was about where I was at this age for my science endeavours. It progressed a little bit more and I went to science camp, actually in Perth, Western Australia, where I did my postgraduate PhD degree. And it was really the first time I'd considered doing research as a career, and not just any research, but radio astronomy research. I think we often hear of astronomy and think of optical. We see these incredible images from Hubble, and often radio is really just forgotten about or not known. So this was really a big life-changing moment for me. And I followed it right through to today, where I moved to Western Australia and actually did my PhD with the same group that I went to visit roughly 10 years earlier. So that's me, very, very exciting. I'm gonna just make sure we can get a bit of a scale of everything. So here is another very accurately drawn diagram of myself. Why I drew it with a lab coat when I haven't worn a lab coat since high school, I'm not sure, but we'll go with it. So we start with us here on the ground in, just human-sized space. If we zoom out a little bit further, we have the world, and in particular I've highlighted Perth because it's obviously my hometown. And if we go even further, we zoom out to our solar system. This is not to scale, please don't judge me. Going even further than that, we have our Milky Way galaxy. And then even further than that, we have this sort of image. We have our universe, we have other galaxies. This image is one of my all-time favorite images from astronomy. For those who have not seen this before or are not sure what we're looking at, this is called the Hubble Ultra Deep Field. So if you get a grain of sand and you hold that grain of sand at arm's length, the amount of sky that covers is this image. And it is at the point in the sky that is defined as the most boring, to use the technical term. So it was chosen this point because there is, as far as we could tell, absolutely nothing in it. There was just nothing happening, nothing that we knew of. And they looked at this one grain of sand for 12 days and 12 nights using the Hubble telescope. And this is what they find. And in this image, we can see two major classes of objects. We can see stars. For example, there's one here. They're the ones with the little spikes on them. So in this image, there are about 4 stars and over 12,000 galaxies. Remember, this is a grain of sand at arm's length in the boringest part of the sky. And what's even more exciting about this image is if you are following JWST on Twitter, you will know that just a couple of days ago, it observed this exact point. So we now have an even better telescope looking at the exact same thing, and I'm going to have a wild guess and say we're going to see even more than what's in this image, which is just incredibly exciting. So that's the largest scale that we have, going really far out to these galaxies and the big structure of our universe. But if we're looking out at the sky to something like this, we're going to see a few dots here and there, some of them brighter, some of them fainter, but pretty much every single one of them is a star within our own Milky Way galaxy. So I want to take a bit of a further zoom of the perfect conditions. If we didn't have Melbourne weather and we didn't have light pollution, what would we see? And it's this sort of an image here. Does anyone know the Aboriginal Constellation that's sort of most notable in this sort of an image? Yes? What is it? Yes, the dark emu or the great emu, which we can see. So right over here is the head of the emu, and then the big body that comes around here, and the tail off towards the side here. So depending on how you look in the sky, this emu can look like it's running across the horizon, and that can also help for the time of year and knowing sort of what phase of life the emus are in as well. But in this image, as I mentioned, pretty much every single thing that we're seeing here is a star within our own Milky Way galaxy. In the best conditions, wonderful dark skies, you're looking at seeing maybe a few hundred dots, right? There's obviously many more than a few hundred stars in our Milky Way, but it's very hard to see them. And in particular, you can see there's a lot of these dark patches around. These are not the absence of stars, but rather the light from the stars being blocked from gas and dust coming through that gas and dust being blocked, and so we just can't see past it. But when we look at the sky in radio colors, it changes drastically. So this instead is what our Milky Way galaxy and our night sky looks like in the radio. You can see that no longer do we have those dark patches. Instead, we see a really, really bright galaxy. And that's because the radiation that comes from that center of the galaxy is called synchrotron radiation. It's incredibly bright at radio, and it's not blocked by the gas and the dust. So we can actually see through our Milky Way galaxy and beyond. It's just incredibly bright, so it's harder to see beyond it. It's sort of like having a giant light bulb in your face and trying to see just beyond it. But the most exciting thing about this image, all of these dots that you see around here, every single one of them, give or take a few, but pretty much every single one of them is a galaxy of its own. So in this image, we see over 300,000 galaxies. That's just a quick look at the sky in radio. You can imagine if we start doing things like the Hubble Ultra Deep Field, but in radio, we get even more, and it gets very exciting very quickly. So what do galaxies look like in radio? Well, let's take this example here. I may get this wrong. I think it's Hercules A from memory. This is, sorry, Centaurus, thank you. Thought I would get it wrong. So there we go, we've got Centaurus A, lovely galaxy here. You can see we've got the same sort of disk shape like our own Milky Way galaxy. And again, it's blocking some of that light from beyond. So we see these dark patches. Now, when we look at the same galaxy, but in radio, we get a very different picture. Instead, we see something like this. So now you can see there are these giant lobes that are coming from the center of that galaxy. In fact, they're coming from right at the center of the galaxy, from that supermassive black hole at the center. So this one supermassive black hole has gas and dust falling into the black hole, going at super speeds, almost the speeds of light or relative to light, And as it's falling in, it's getting superheated, getting incredibly bright. But the black hole itself is spinning and it has a magnetic field, and through some very complex physics that no one quite understands, the black hole then emits it again. So we have this swirling storm coming into the black hole, and then these two big ejections coming out in opposite directions. And that's what we see, these sort of bits here. These are called the jets coming from that central supermassive black hole that then blossom out into large mushroom-shaped clouds that we call the lobes. So that entire structure is called a radio galaxy. And it can extend well beyond the size of the actual host galaxy, sometimes up to 2 million light years across. And in fact, as we get bigger and better telescopes, that 2 million light years doesn't look like it's an upper limit. It looks like there are even larger ones out there. So this is really an incredibly vast structure that we're looking at with radio. And that, if we go back to this image here, every single dot here is that structure. We're looking at those big double radio lobes, but they're all just so far away they look like dots. You can see sort of just underneath the legend that we have over here is one that's pretty close to us, and you can actually see the full structure there. So that's what a radio galaxy is. Let's have a little closer look at them. And as I mentioned here, we have the core right at the center, so that's that supermassive black hole, and then the entire structure end to end for those lobes, about 2 million light years, but probably more as well. All right, so what does that look like in radio color? If we look at various different wavelengths using radio light, what do we see? Is it the same image? Is it just as bright? Well, it turns out it follows a pretty simple thing called a power law spectrum. So it's really bright at radio red, and it gets significantly fainter as we head to these higher frequencies. This is quite boring, just a straight line, but we do see some others with different shapes. So sometimes if this galaxy is incredibly small, really small, I say that in astronomy terms, really small in this sense is about 30,000 light years across. So it's still large. But now we're talking on the scale of the host galaxy itself. So those big lobes are no longer well beyond the galaxy, but actually within the galaxy. And if you look in radio color now, we see a shape like this, where it's really faint at red, it gets very bright, and then it gets faint again. And because this entire thing is called a spectrum or radio spectrum, and this has a peak in its spectrum, we give this a very creative name of peaked spectrum sources. And I'm sure many people in this room are familiar with how astronomers are not great at naming things. We have this telescope. Does anyone know what this one's called? Yes, the VLT, Very Large Telescope. And then astronomers, being astronomers, we always want to build bigger and better. So we built something larger, and we're like, well, you can't have the Very Large Telescope and then a different telescope bigger than that. So we built something else, or we're planning to build something else called the Extremely Large Telescope. And there is actually a plan for an overwhelmingly large telescope, but I think that one didn't get funding, which thank goodness at that rate. It's just embarrassing for us. And you would think we learnt our lesson, but no, because if you look at stars, you have red giants, you have red supergiants, you have red hypergiants, and you have red colossal giants. And then the exact same with blue stars, blue giants, blue hypergiants, blue colossal giants. So it's a bit embarrassing, but at least we're consistent, so it's all right. Right, so our peak spectrum sources, these really compact galaxies. Well, how do we tell the difference? It's nice with a little rhyme. So these really big ones are very red. They're really bright in that radio red, whereas the young ones are very bright in the blue. They're often quite young in that sense. So which little galaxy are you? We look at the radio colors to help us understand how old the galaxy is. And that is where my favorite little telescope comes in. So this is the MWA that you mentioned earlier, the Murchison Wide Field Array. You can see it looks very different to what you would expect for most radio telescopes. It's not this big dish shape. Instead, we see these spider-like antennas, and they are far cheaper to produce, so that's very exciting. And it does mean that if one gets knocked over by an emu or a kangaroo, we can just come and stack it back up again, no worries. Easy as. And in fact, you can see some other really high technology implementation here of the rocks holding it to the ground. So we do very well in radio astronomy, as you can see. But these are all the cables that I was also talking about. There's just a huge amount of cables. And in fact, end-to-end, MWA has just gotten an upgrade where these sort of groups of antennas that we see, you can see they're kind of grouped together all over the place. The furthest distance from end to end is about 5 kilometers now. So you have really long cables traveling pretty large distances, and you will need to replace them at some point anyway, so it's just not worth digging trenches to save them from the sun bleaching. Right, so we have our wonderful peak spectrum sources, and what I did was a survey of these sources, looking at what they looked like in 1 year to the next. Now, I did mention they're really, really, really tiny, but they are 30,000 light years across. So that does mean if we're looking at seeing how they change and evolve, realistically, you should be watching them on timescales of about 30,000 years. They should be taking about that much time to show any dramatic change, let alone the ones that are bigger than that, about 2 million light years across. They shouldn't be doing anything, certainly nothing that we can see. So I did a quick survey just to make sure the telescope was behaving and the galaxies were behaving, just make sure everything was as we expected. Looked at a lot of these galaxies and found in 1 year they looked like this, and in the following year they looked like this. They got incredibly bright. That was not what we expected to see. And in fact, I saw some that looked like this in 1 year, and then they looked like this in the following year. I saw ones that looked like this, a nice old galaxy, and then in the following year they were like, just kidding, I'm a baby. So everything seemed to be out the window. All these things that we understood of these galaxies that they shouldn't be changing, certainly not on observable timescales, let alone 1 year, and they seem to be aging in the wrong direction. Now, as a very young and poor PhD student, I was very excited that I had found the universe's best anti-aging cream, and I was about to make some mega bucks. But I obviously had to figure out what was happening, how is this going on, and how can I then use that to figure out what's going on with the galaxies? Well, this is just an example of exactly that galaxy. So in the first year, you can see the pink. It's showing that really lovely peak. And in the following year, it's just going straight up. Now, it might peak somewhere over here, but again, that's going in the wrong direction. We're not expecting it to peak at even bluer directions or bluer colors later on in life. It should be going redder and redder and redder. So all of this was very weird. Right, so what's going on? Questions from the audience here. Does anyone have a theory? Precession? That's a great idea, but alas, no. The way that we take the observations, they are actually taken over a year and kind of added all together, so any kind of precession would be averaged over. Also, the Murchison Wide Field Array, certainly not known for its accuracy and location sometimes, has a very low resolution. So if there is precession, we would absolutely not be able to detect that. So no. Any other ideas? No? Sorry? Expansion of the source or the universe or both? Either or? Yeah, it could be expansion, except that again, that's meant to be taking thousands and thousands of years. So if it is that, that means we have to seriously reevaluate our understanding of galaxy evolution, because we thought that process was at least tens of thousands of years, if not millions. So it could be, but goodness me, I kind of hope not, because I only had 3 years funding, you know, so would like it to be at least something simple. For expansion of the universe, again, unlikely given the amount of change that we're seeing on the timescale we're seeing. So that really short timescale just makes things very difficult. All the processes that we had that explained variability in radio colors really shouldn't be showing any variability on short timescales of a year. We expected timescales of tens of years, decades and decades, really. At the very, these are extreme events changing. All right, so my first thought, and in fact, this is a bit of a shout out to a very famous astronomer, an idol of mine, was that it was a little green man, or an LGM. So Professor Dame Jocelyn Bell, when she first discovered pulsars, so these rotating neutron stars that kind of act like a lighthouse in the universe, and she saw these pulses of the light coming from these pulsars, had no idea what it was, but it was incredibly regular and really very bright, and she could easily see it all the time. Thought, this must be aliens, I'll put down little green men. And there's actually photos of her original notes of seeing these observations and writing down, that's another little green man. So I thought perhaps I'm having something similar. Maybe that's what's going on here. But realistically, I know there are conspiracy theorists out there. Astronomers don't have enough money to be hush about finding something like a little green man in real life. So this is not the case. So instead, we actually have to go to an old, wonderful nursery rhyme that is actually scientifically accurate. So if everyone recognizes this, Twinkle, Twinkle, Little Star. This is actually a scientifically accurate nursery rhyme or song, whatever you want to call it. And the reason is because of that first line in particular. So let's delve into that a little bit more about what twinkling is. Let's start with, we have the Earth again. Here we are, and we have our distant star all the way over there, very, very far away. As the light comes from the star towards us on Earth, it travels through the Earth's atmosphere. And the Earth's atmosphere is very turbulent, so as that light passes through the atmosphere, it makes the star look like it's changing, and see this twinkling effect. But it's not the actual star itself that's changing. It's only the light that's changing as it passes through the atmosphere. This is a process called scintillation, and there is just pages and pages of maths about it. Really fun. So this process, this Twinkle, Twinkle, Little Star, works because this is a star. If you change that to a planet in our solar system, you'll notice we don't see the planets twinkling. And that's because from our perspective, the planets look much larger than the stars. Obviously, the stars are physically much larger than the planets, but because the planets are so much closer, they appear much larger than these very distant stars. And in fact, that is critical for whether or not something will scintillate or will twinkle. If something appears too large, it won't twinkle. Everything kind of gets averaged out, and you just see the same static image. So that is why Twinkle, Twinkle, Little Star is in fact scientifically accurate, and it doesn't say Twinkle, Twinkle, Little Planet, which would be very wrong. Right, so how does that apply to our circumstances? If we have our wonderful radio galaxy, and again, us here on Earth, as the light from that distant galaxy is traveling towards us, it's passing through a lot of things. In fact, it's passing through, most importantly, our own Milky Way galaxy. So the gas and the dust in our own galaxy, as the light is coming through the galaxy itself, it's changing that light. So the galaxy itself isn't changing, but the light is changing as it passes through our own galaxy. And so this is still scintillation, and mathematically speaking, is exactly the same as the twinkling of stars. The only difference is that now, instead of the Earth's atmosphere causing that twinkling, we're seeing the twinkling because of our own Milky Way galaxy. And in fact, you can also see the same effect for galaxies that are the light's changing because of solar wind from our own star. That's a process called interplanetary scintillation, and was also discovered by a woman, Margaret Clark, in her PhD thesis. So again, I was like, I'm on the right track here. I'm finding some good things. Right, so could that explain what we're seeing? This process of scintillation could happen on these really rapid timescales of about a year, rather than the tens of thousands of years we need for the actual galaxy to be changing. And it turns out for these ones where we see the galaxy get changing shape like this, so it changes its color, that cannot be explained by twinkling. Twinkling can only change the brightness of the entire source. It doesn't change what color it is, you just see it getting that sort of flickering effect. So we can't explain this, but it can explain those ones that are getting brighter and dimmer. So perhaps we've solved part of the puzzle there, but not everything. So that also means, though, all those galaxies that were twinkling, or that we think are twinkling, must be very, very small. So that rules out those really, really big ones. And it must be that we're seeing these really confined galaxies that are small but also old, perhaps, because we see these twinkling ones that are old, but then they have to be small if they're twinkling, but they can't be small because they're very old. So all of that doesn't make sense. So instead, what if we have these galaxies that are not quite as old as the big old ones, but also not quite as small as the small ones? Perhaps they're growing and they were trying to grow, but they kind of got blocked by something. And so they're surrounded by this medium around it. in this scenario, instead of having the really compact ones that we call young, or these baby black holes, instead we call these the frustrated teens. So they are being frustrated by their environment and prevented from growing. Could that explain what we're seeing? And it turns out we need a bit more information. Enter the square kilometre array. This is the one time when astronomers had the opportunity to be really creative. We're building this incredible telescope, and as we've learned, we're very literal with our naming. But unfortunately, this is not a square. This is also not a kilometre, but it is somewhat kind of an array. So maybe 1 out of 3, I'll give it. Very unfortunate and doesn't go with the theme of things in our naming conventions in astronomy. So using the square kilometre array, we can start to look at these galaxies, watch them in lots of different radio colours, and start to see, is it because these are frustrated, angsty teens that are interacting with their environment, and that's causing them to change colours and evolve on really rapid timescales. And this is the prototype for that. So this is the AAVS that I was talking about earlier that Facebook missed, sorry. But this is our testing array. So this is the design that their square kilometre array at low frequencies will have. It's being built here in Australia, over in Western Australia. We call these Christmas trees, and in fact there are a few in the office that we often decorate for Christmas, which is very exciting. There's also, you can see in the background here, a nest for a wedge-tailed eagle, ginormous. So these fun little Christmas trees, the square kilometre array is planning on rolling out 100,000 odd of these, in fact about 400,000 of these. So the MWA has a couple of hundred, if not, where are we at now? Maybe a couple thousand, but we're looking at increasing the number of arrays by at least an order of magnitude. So these Christmas trees, it is going to be a poor PhD student who's just sitting hours away knocking these together. Thankfully, I'm done with that part of my life, so won't be me. Right, so what do we see when we look at galaxies in radio? I do want to say I've shown some pretty gorgeous images tonight. Unfortunately, not all of them look like those big, beautiful double-lobed structures. In fact, the vast majority of my galaxies look just like this. A little fuzzy blob, you can't really see too much. That's especially the case for those really baby ones, the really compact ones that are also really far away. So often in order to see that structure, you need to have telescopes that are about the size of the Earth. And in fact, a later part of my PhD was connecting telescopes from New Zealand, Australia, and South Africa together to act as one big telescope so I could see that structure. So this is taken with a telescope just outside Sydney called the Australia Telescope Compact Array, or ATCA. And it is a lovely round blob. It's actually behaving very nicely. This is a lovely image. Now with the MWA, that's not necessarily the case. Now the ACRA is those classic dish-shaped radio antennas, and so it can point at a very small point, and it doesn't see much else. It's sort of looking just at that point, and it doesn't see a large fraction of the sky. That's unfortunate if you're surveying the sky. It would obviously take a very long time, but really handy if you just want to look at one galaxy or two. The MWA, this is another one of my wonderful galaxies that you can see less nice, very elongated, and in fact, that's actually not real. That's an observational effect. Really frustrating. So not all of them are even those nice blobs. Now the MWA gives us images like this. You can see this is very, very different. And there's one thing in particular that I want to point out for this. So firstly, let's see, there are lots of these dots here. And that's because this is now looking at a really large fraction of the sky. So it covers it's about 30 square degrees. This is really quite large in one go. So in a 2-minute snapshot, you can find over 200 galaxies in just one image with the MWA. So that makes it fantastic at surveying the entire sky. Really unlucky if you are only interested in that dot there and you see everything else. The other thing I want to point out is you can see there's a lot of streaks that are coming from the right hand of this image. That is also not real. That is really unfortunate. That means that there is something in the way. So I put together all of my images because, very sad, I don't want an image like that. So this is a lovely image. This is best case scenario with the MWA. You can see we no longer have those streaks. There are lots of these dots around the place. You can even see ones like this that look like it's that little double structure, those two lobes. And this is the one where, best case scenario, we're seeing over 200 galaxies in this one image. This is just from 2 minutes of data, so pretty incredible. But you can see it does look very different to that other image. So I patched them all together to have a little look at what we were dealing with here. You can see it doesn't look great first glance. Certainly not that beautiful radio image of the sky that I showed at the beginning of the night. But there are still dots, but there's a lot of these sort of old school TV, black and white, static. That's not what we want either. And one of the biggest issues was the fact that I was seeing these streaks across multiple images. And that's a result of sources like this. This is called Fornax A. You can see there's even the bright bit in the middle and then the two lobes either side. This is a beautiful example of the radio structure and those big radio lobes. But you can also see that there's these kind of fuzzy patches coming out from it. And that's because it is so bright in radio colors, and we're seeing the sort of connected, sort of the overall combination of all of these galaxies. We're seeing what they do to this telescope in one go. So Fornax A being that bright is kind of drowning out everything else. It makes it really hard to get a lovely image of all the galaxies around it, but you do get a lovely image of Fornax A. I don't care about that one. I want the baby ones. So that's really annoying. But thankfully, we have some really fancy code that I didn't have to write, thank goodness, that deals with these ones. There's only a handful of them. We know them quite well, and we can actually subtract them from our data before we take the image, and then it doesn't make as much of an issue. So this is not actually as frustrating as I make it sound out. What is frustrating is this one, which we are going to call for now the source, right? You can see the same effect. This is an incredibly large source, very, very big, very, very bright, that's causing these fuzzy blobs all around the image. It also made it very hard to detect very faint objects in this image. So I really wanted to get rid of it so that I could actually look at the galaxies that I wanted. Now, I mentioned we only know there are a handful of these really bright ones, and we know them quite well. So I had already subtracted them. So who's this? What are you doing? And I really just wanted to know what it was, not because I was interested in it at all, but because I wanted to get rid of it. So I asked my supervisor, and she said, oh, it is probably this other one that we don't have routinely being subtracted, called 3C044. I was like, oh, of course it is. That was my first guess. But no, that's what 3C44 up there is. So she's pretty close, but not quite. That teeny tiny little dot there, that is 3C044. So what is this? So big, so bright, very confusing. I decided to look back in some archival data to see what did it look like before, and also in the catalogs associated with that, because you would have had to deal with it. So what did you call it? And I can then do the same. So I looked back at these past images. This is the exact same coordinates. There is nothing there. Now, I got very excited. What do you think it is? It is not Jupiter. It is not Jupiter. I was so unbelievably excited because I thought it wasn't something as close as Jupiter. This is something that has appeared in about 10 years' time, really bright, very, very cool. So I went to take note of the observation ID and come back to it later. But I'd already texted my colleagues at this time being like, everyone hold on to your hats. There is something big here. This is cool. So when I went to take a note of the observation, anyone want to take a guess at what it is? It's the sun. Yes, right at the top here is the sun. Because in radio astronomy, you can observe during the day. Really convenient. It means I don't have to stay up all night. But if you forget about it, then you deal with the sun in your data, and you also forget that you're observing in the day in the first place. So I then had to go back to all my colleagues and say, hey, remember that really big thing I was talking about? Don't worry about it. It's okay. Don't ask any questions about it, though. Thankfully, apparently, this is very much a rite of passage in radio astronomy. There have been many astronomers, including Nobel Prize-winning astronomers, who have put out big notifications saying they've discovered something only to have it be Jupiter or Mars, and even one time the moon. So I only told a few people. I didn't get that far, thank goodness. But I still have very conflicted emotions about the sun, frankly. Not just because I burn very easily, but ruins my data. So on that, I will just leave with this beautiful image of the next generation of our survey. You can see here this radio color. There is lots of patches of blue. There's these patches of red, and those colors are actually telling us about the object itself. Is it a baby galaxy? Is it an old galaxy? Perhaps it's one that's changing because it's frustrated. And in fact, these sort of bluish bubbles are related to things in our own galaxy, these big nebula style things. And now my current job is making the next generation of this survey. So we initially, the first version of this survey, surveyed the entire southern sky, and we found over 300,000 galaxies. We published that to the community to just use for whatever science they wanted. Now, when the MWA got an upgrade, so it doubled the length of the baselines, or sort of expanded the size of the telescope by 2, we now have even better resolution. We're much better at processing all of the data, and we did a sort of test patch of the sky with this new and improved telescope. And in that region, that was about 5% of the sky that we covered in this image, we found over 80,000 in just 5% of the sky. So big things to come, particularly in Australia in radio astronomy. And with that, I'll take any questions you have. Thank you.
Thank you, Kat. Have we got some questions from the audience? All stunned. Yes.
Thank you. I just wanted to know what the image had in it. There, it looks like bubbles in space. Is that it? Underneath?
Like, for example, there's a
there,
teeny one there.
and then-
There's quite a few over here.
Yeah.
Those ones?
Yes.
They are, in fact, bubbles is actually exactly how we describe them, because they look just like bubbles. And yes, really good spotting. These are supernova remnants. So another really great thing about the radio, when we see these supernova explosions from a star dying, and it has this huge ejection of explosion as it dies, and it creates this kind of shell as it expands. That's visible in optical for a few days, maybe a few weeks if you're lucky. And so you really have to catch it right as it happens and then watch it happening and watching it evolving. Now in radio, these can stay bright for hundreds of years. So in fact, there is a lot of research going on. From this image, we were able to find a lot of these supernova remnants that hadn't been discovered before because we missed the observations because they were hundreds of years old, and we couldn't see them anymore with optical telescopes. And so now we use these bubbles and we estimate the size of the bubble and how far away it is, and try and pinpoint that to historical archive records of when older civilizations said a star appeared in the sky. And that can help us estimate how old that was, where in the sky were they looking, is that this bubble? And we've been able to identify a few of these old apparent stars that appeared out of nowhere as being these supernovas. Yeah. Great question.
Great talk.
Thank you.
Whenever you've shown the pictures of your arrays, there's a grid mesh on the ground underneath. What's the purpose of that?
Yeah, a really good question. It has two main functions. Firstly, it actually acts a bit as the mirror would in a telescope, and that sort of array part. So it actually, as the radiation comes from the universe and from the sky, gets onto this mesh and is reflected into the actual antennas that we want. So it kind of acts a bit like focusing it. The second very useful thing that it does is allow us to put the telescope somewhere instead of just on the dirt. Click it in. So very handy. So yeah, having that mesh down, you're able to kind of place them in this very regular grid. That means they're all spaced very evenly as well, which is very important for processing. If the array is slightly different, that can make all your calculations wrong for processing. So having that mesh is very helpful, but also essential in order to actually get the observations as well. What was that, sorry?
How secure are the antenna to the ground itself? And what's the maximum wind velocity that they can take?
Yeah, a good question. I wouldn't know the exact number, but they're quite secure. So they actually have clips in to the mesh, and as you see, we've got the rocks down so that the mesh isn't going anywhere. And there are zip ties and stuff as well. Wind is not really an issue in that sort of area of the outback. We do get storms, but the bigger issue is lightning more than anything, and very occasionally some flooding. But yeah, winds is not as much of an issue. The bigger issue is like emus and kangaroos knocking them over, which frankly, no amount of our work is going to stop that. They're going to knock it over if they want. But interestingly, in the Netherlands, there is a sort of sister telescope that's very, very similar, has the same spider-like antenna design, and that's called LOFAR, the Low Frequency Array. Except if you look up images of LOFAR, you'll actually just see these really big black boxes on the ground. And that's because the Netherlands has a very different problem than the outback of Australia, in which case, we're dealing with sun bleaching and emus. They're dealing with flooding constantly and swampy regions. So these big boxes are to essentially deal with that, with the wind, with the rain, and lock them in place pretty stably. Yeah.
What's the frequency range
Of this image, this one is from about, the frequency range is 72 megahertz up to 231 megahertz. So that was also why this is really exciting, because it is such a low frequency that we haven't really been able to look at on a large scale before. And so part of the reason we even found all this variability was A, no one thought to look, and B, we didn't have the technological capabilities to do that beforehand. So any sort of variability survey before could only look at one color. And we can see in radio color, which as you saw is really important for seeing the changing shapes in those spectrum. But the low frequency side of that also made it particularly interesting because you're probing or you're really sensitive to finding the even more extended structure. So as you go to lower and lower frequencies, you're kind of more sensitive to further and further away from the black hole. So at the higher frequencies of around gigahertz and higher, you're probing closer and closer right at the actual black hole itself and that accretion disk. But at hundreds of megahertz, you're looking at the really extended lobes. So the fact that we saw it changing on year timescales was even weirder because it was these low frequencies. Whereas at the higher frequencies, it's a smaller structure, so it can vary faster. Yeah.
Over a period of time, how long before you actually have to recalibrate?
Recalibrate the telescope?
Yeah.
Well,
Would it be years, months? Or anything?
within the night. Yeah.
Oh.
Yeah, and partly that's because of the frequency range. So that low frequency, very exciting for science, really frustrating for the ionosphere. So particularly right as the sun sets and right as the sun rises is where the ionosphere gets particularly turbulent. And so you'll actually see the positions of these galaxies moving a lot, and they also get distorted in different shapes. So sometimes you think you've seen a really weirdly shaped, very exciting galaxy, and it turns out actually just the ionosphere that night was terrible. That's also particularly bad when the sun is in a solar maximum, because you see more wind coming from the sun, more solar wind, that causes that ionosphere to be more turbulent. Thank you, that was the word. So you see more turbulence in the ionosphere. So we're actually heading into that solar maximum now. A lot of the observations for this survey were done in a solar minimum, so it was really lovely. And now we're looking through the data and seeing these nights where we had a really bad ionosphere, and it's almost impossible to calibrate on. And so we're looking at re-observing, except that it's actually just getting harder and harder as we get to the solar maximum. And so potentially we just have to wait 10 years until we can start to do the same sort of survey. Yeah. The sun again. My arch nemesis.
There's been a lot of talk with optical astronomy, all the satellites going up. Does this cause any problem for radio astronomy?
You have no idea. I have no idea. A certain man who shall remain nameless, who has a love of cars, we shall say, launching many, many satellites up, and said, don't worry, you'll only ever see them at dawn and dusk, so it won't bother astronomy. A lot of things wrong with that. Firstly, in optical astronomy, dawn and dusk is when you take your calibration. So if they're there in your calibration, that actually ruins the entire night. Secondly, you can't predict that they're going to stay that way for very long because of the orbit that they're in. So it's actually degrading very quickly, which means they'll start to get more and more unpredictable in where they are. And lastly, that's all optical. In radio, it is a whole other story. So a mobile phone on the moon is 300 times brighter than the brightest radio galaxy. So if you imagine a satellite, which is much closer than the moon, much larger than the moon, rapidly going around all the time, and in fact moving a lot, that's a really big annoying part, moving through your image, it essentially ruins the entire data. You saw the issue that the sun had for being as bright as it was in radio, of just destroying that image, and that's at the same coordinates. If you're seeing something like that moving around, essentially that observation can be irredeemable. You can't get data from it anymore. So as we're launching more and more of these satellites, radio astronomers are screaming very loudly, please stop. Or if you are going to do it, be a bit more careful about it. So making sure you are aware of the orbit, you can set the orbit, and you can also change the orbit. And then when you're done with this, find a way to be able to actually bring it back down to Earth. Don't leave it continually up there orbiting forever. So that's a really big issue with space junk. But beyond that, the biggest issue is it's actually becoming more achievable to send satellites up, which means that you're seeing a lot of universities sending these satellites up as student projects. Fantastic, I love that, a great student project, very exciting, but it means that there's not a lot of regulation around what frequencies they emit. So because it's a student project, they're really, we're just sending up something, this is really cool, whatever, it's done now, that's that. No, it's still up there and it's still emitting. And if you're not really careful and really firm about keeping these particular frequencies blocked out for radio astronomy, you see the bleeding effect of these satellites that are mostly okay, but are still bleeding across. And they're like, well, it's only like 10% of our emission. 10% of how bright a satellite is for us is still a lot, it's still a bit too much. So there are protected frequencies, but yeah, there's a lot of bleeding as well. And so ideally, stop launching satellites. But also I like Wi-Fi, so I don't know, it's tough. Yes?
We just had a couple of quick online questions
Amazing.
as well. From Osmonday, asking if you're concerned that the eagle will get fried by the radio waves.
A really important question. And it's not often that astronomers have to do ethics reviews, but don't stress about the emu. The emu will be fine. In fact, the energy of the radio waves coming in, I usually am outside sort of doing this talk, so it's weird to be inside, and I could just imagine like a handful of dirt or something, of rocks. All of the radio waves that we've collected since we started doing radio waves, all of radio astronomy, all of that energy, if we converted that into energy from every single observation of radio astronomy since around the 60s or so, it would be the equivalent of me getting a handful of rocks and dropping them from my height. That energy, that potential energy from gravity, is roughly the same as the entire energy that we've collected through all of radio astronomy. It is not much. So you can kind of think that it is these, we see the big wires going around and you touch it, a lot of voltage, you're dead. That is not the case in radio astronomy. It's really, really low frequency, really low energy. And so the emus are safe, don't worry. It is the telescopes you should be worried about.
And another one from Steve, a question, when do you expect the upgraded MWA survey to be completed?
Oh, that is dependent on how quickly I work, which, I hope my boss isn't listening. So we are hoping, we've already processed some of this and done an initial release of 5% of the data, but we still have a lot more processing to go. So it should be within 3 years, because that's as much funding as I have. So within 3 years, hopefully a lot sooner than that. We want to get it out to the public really as soon as we can, because the sooner it's out there for everyone to use, the sooner we see everyone using it for science and we get to see what comes out of it. So ideally, it's also a little dependent on how much supercomputer time we get, because you simply can't process this on desktops. And so hopefully it will be mostly processed within the next year or so, and then released to the public not long after that. Depends how fast I can write a paper. Yeah. Yes. It's in Perth. So ASCAP and the MWA are both in the Murchison Radio Astronomy Observatory as far away from everything as possible. And then there are large wires to come all the way down to Perth. In fact, it was one of the reasons why Perth had the NBN before the rest of the country, and everyone was like, Perth, of all places. Why? Radio astronomy, you're welcome. So we needed the NBN to be able to transport it all. And the supercomputer that we're using is the Pawsey Supercomputing Centre, which is a public and free supercomputer. You apply for time to use. And it's just across the road from my office. So when it doesn't work, I can go over the screen.
Is it pre-processing?
Some pre-processing before the supercomputer. That's mostly things like, so as the antennas are collecting the data, you can see if something's over here and you've got to tell, a little array here and a little array there, the light from this will hit this telescope before it hits this one. So that's called the delay, and we calculate that delay and sort of add it all together and then send that signal off. Yeah. So another question at the back there?
Yeah.
Yeah.
Can you tell me what is the most distant radio source detected so far?
Well, that's a tough one because it's actually changing very frequently at the moment, and partly because of JWST. So JWST is not like Hubble, which is purely optical. JWST is also infrared. So it does go to slightly lower frequencies, and as a result, it can see sort of further away as well. And so we measure things in a scale called redshift, which essentially measures how much the light has been stretched due to the cosmological expansion of the universe. And so those really far away things have a higher redshift. Half of the universe has a redshift below 1. The other half is everything else. And I think the furthest away from JWST in the recent images that came out, there was a theorized 12 redshift, which is obscenely large. But before JWST, and that's not quite been confirmed yet, before that, I think the highest redshift was maybe 9 or 10. And that's actually pushing the boundaries of what we think was possible with the evolution of the universe. We didn't think galaxies could form that early on in the universe. But I don't know what that is in kilometers, light years, or anything that makes sense. I only know redshift. Sorry. Yeah.
How close are we getting to the start of some universe 13.8 or 7 years ago?
Mm-hmm.
Does using great observations enable them to get
Closer and closer.
That particular time, looking back in time,
Yeah.
close enough to that.
Yeah. Yeah, that sort of age of the universe. Yeah. So two things. In terms of getting back further and further, we've kind of actually already gone back as far as we can, and that's the cosmic microwave background. So that was the moment that we sort of see the universe frozen, or this sort of image of the universe frozen at the youngest possible time that we can observe. Anything younger than that, it was simply too hot. There wasn't any emission. It was just kind of this soup of stuff. So the cosmic microwave background, we've gone back as far as we can. We can refine that, but we've already seen it. In terms of radio observations getting close to that and seeing, actual things rather than this kind of frozen image of the universe, radio is very much helping with that. So there is a theory, or not a theory, but a field of radio astronomy called the Epoch of Reionization. And that's the stage where we have enough stars in the universe that have caused the atoms in the universe to ionize, where they've ejected an electron and they've got an overall charge now. And so that epoch of reionization, we believe it's there. We believe it has to have happened at some point, because we see before that it is non-ionized. We see this, nice neutral universe, but then we look at now and we see an ionized universe. So at some point, it had to become ionized. And there's a lot of theory about when that happened. And was it something that happened very quickly, or was it something that really took a very long time? And the frequencies we need to test that is right where the MWA is testing. And so this is actually something that the square kilometre array is going to be looking into, because the MWA, all of this research using it, has really helped us understand what we're looking for, what sort of signals we need to get, but it's also shown it's just not good enough. We need something better. We need the square kilometre array. So all of these observations are pushing that limit lower and lower, but they've not actually detected this epoch of reionization. It's just theorized, and we know that it had to have happened in some way, but we've not been able to detect it yet. And hopefully the square kilometre array answers that. Yeah. Mm-hmm. Yep. Mm-hmm. Yeah, he was one of the people that was able to show that it's accelerating and not decelerating. So that still fits in with that model. And part of the issue is that there's still a lot of a debate of how do we measure that expansion and how has it been throughout the history of the universe. And so that does also make things difficult in trying to estimate the time frame that this epoch of reionization happened. And so that can make the detection harder. But it does still, it all fits in together. Yeah. Yeah, that's exactly it. Yes. Yeah. Mm-hmm. Yeah. Yeah. So for anyone who missed that, talking about measuring the constants that measure the expansion of the universe. There's two main methods that we have to measure this. Don't ask me details, I'm not a cosmologist, but there are two very different ways to measure it. And if you look at the Hubble constant that's measured from these two different methods, they are not the same. They are consistent with the other measurements taken with that method, but not across methods. So either there's something wrong between the methods, or there's something that we're not accounting for, something that happened in the universe that we don't fully understand. And ever the drama queens that we are, this is often referred to as the Hubble catastrophe, because we don't know why they're different, but they're different. And in fact, one of the new theories or new methods is using gravitational waves to try and measure the Hubble constant. And this is a big point of contention because who's it going to agree with? What side? Is it going to choose a whole different one? Very exciting. There was an initial measurement of the Hubble constant done with gravitational waves recently. And unfortunately, because it's still very early days to be doing this, it had such large error bars that it actually was consistent with both methods. Really unfortunate, just sort of smack bang in the middle, but it also could have been either or, we really just had no idea. But it does hint that if we get better at measuring it in that method, perhaps we'll have a different way to kind of test each of those ones. Yeah. Yep. Yeah. I have absolutely no idea on that figure, but because supernovae, and in particular type 1 supernovae, are so incredibly energetic, it seems weird that you could see a single star dying in a distant galaxy. But in fact, we can see that. And so I do know that you can get quite far, but I don't know the exact number. I work on the galaxies themselves, not what's in it. That's too small for me. No, I want bigger and better, more exciting things. Before you ask the next question, I'll just see if there's any other questions in the room, just aware that we are
There's another quick online one.
Yep.
From Oz Monday. Radio astronomy doesn't really allow for an image to be observed without it being processed by a computer.
Mm-hmm.
Like an optical telescope is an instant view, so to speak. How long does it take for an image to be processed with radio astronomy?
Oh, that's a very good question. And it sort of depends who you ask and also what radio telescope you use. So in my PhD, I used a variety of different radio telescopes. So the Murchison Wide Field Array, which I've obviously talked about a lot. I mentioned the ATCA as well, Australia Telescope Compact Array, and that one that sort of collected 10 telescopes and acted as though they were one big one. So I've kind of got my finger in all of those pies to assess the easiest and the hardest. The ICRAR is by far the fastest to process. You can actually just do it on your laptop. You really don't need anything fancy. The main time-consuming factor there is writing the code up to do that, but because the ICRAR has been around for long enough, we actually have a really good pipeline that sort of does this mostly for us. And so it's really just your own personal time of you clicking go and checking things and checking that it's behaving nicely. So for some of my research, I monitored 15 galaxies with the ICRAR at a range of different frequencies, and I did that multiple times during 2020 to see this variability. So I had something like 20 gigabytes of data to get through for each epoch, and I had 5 of them, I think. So 20 times 5, around 100 gigabytes of data, but I could process that in a couple of days for each epoch. So it was really quite speedy. The MWA is somewhat speedy, definitely takes a little bit longer. The fact that we have that large field of view is what really slows it down, and that's also why you need the supercomputer. So if I was doing that on my laptop, it would just be far, far too long. I wouldn't be doing it in my PhD, that's for sure, let alone doing the entire survey or any kind of variability. It would just take years and years to get through. Just the pure processing time, let alone actually doing any sort of quality control or checks. For things like the LBA, the imaging process is somewhat the fastest of it. The slowest process can often be getting the data from the telescopes to where I can process it. So this recent image of the black hole that we have, Sagittarius A star, and also M87, the classic donut shape, they were really held up for a long time because one of their telescopes is way down in the South Pole, and they had to wait till they could get a ship to transport the hard drives back to somewhere where we could deal with it. So sometimes the delay actually comes from literal transportation issues, but in terms of the raw processing from getting that data to an image, depending on the telescope, it can range from a couple of days through to months or years. Yeah. About what, sorry? I have no idea what that is, so I don't know. Oh, yes. Well, actually, there is someone at work when we have a separate office for students that they come and go and the computers stay there. And they have a program where they've just taken those computers for themselves and started processing. It does make things faster, but realistically, we really need very, very good computers. And you also need to have very good scripting that understands the computer you're working with. So if you're having these community source ones, so long as it's a very consistent structure and it's really understandable, it should be fine, it should be usable. But often it's better to have this dedicated team who are specifically working on maintaining that supercomputer, checking that it's running things. So the Pawsey Supercomputing Center has, the entire group of people working there to make sure that it's still running, but also scheduling different things so it's all processing together, which is definitely very useful. And I think we could absolutely use this grid computing, but it would need very careful scripting and planning to make that work. Yeah. Any more online questions? No?
Kat, thank you.
Oh, yes. So I am a roller skater. I actually play roller derby, and given my last name is Ross, I actually have a derby name. My derby name is Ross and Roll, which is obviously very fun. I picked up in COVID. I thought it would be great, given I wasn't allowed to go anywhere or do anything, I'll learn to roller skate. And then when COVID's over, I can skate into work and look super cool. That'll be my plan. So I bought a pair of roller skates, and the second time I ever went on them, I fell backwards with my arm outstretched, and I very much hurt my elbow, went to the hospital. Turns out it was dislocated and just tore everything in the elbow. It was just a nightmare. The surgeon said to me, if you so much as even lift up a plate of dinner, your elbow will just pop out. So come and see me in 6 months, and we'll look at pushing yourself out of a chair in 6 months. Otherwise, don't use it. And the way that he broke that information to me was, what do you do for a living? And I was like, oh, I'm a student. He was like, yeah, but in what? I was like, in astronomy? He was like, oh, that's fine. I've never met an astronomer that needs both arms. Terrifying. So after about a year or so of rehab, finally got my elbow back to strength. And because I am incredibly stubborn, back on the skates I got. Very exciting. Signed back up for Derby, and this time learnt how to fall properly, because you should not fall backwards. You should always fall forwards. And was doing great at that. And then I signed up for artistic skating as well. And I signed up for a competition. It was my first one. So I decided to do the lowest level, thinking that they would break everyone up by age. They did not. So I was up against all these 5-year-olds who were very excited to be at their first competition as well. And right at the end of my circuit, I decided to end in a flourish, for the judges, get those extra points so I can demolish the kids. And I fell backwards with my arm outstretched, and I dislocated my arm. So then I had to email my physio and say, hey, I'm back. And I went through the same thing and got another scan on that one. And the surgeon so lightly put it that my ligaments were flapping in the wind, which was lovely news. And that one I actually went into surgery for, where they spent a couple of hours just checking how strong my elbow was, and then said, oh, actually, we couldn't dislocate it, on your way. And there we go. So my elbows are now in tip-top shape, and I am back on skates because it's going to take more than that to stop me. So, but Ross and roll has kind of become a bit too literal now. It feels like I'm rolling onto the ground, injuring myself. So anyway, yes, thank you, Andrew, for that.
Well, thank you, Kat, for a very interesting talk with a very unexpected finish. So thank you for filling in, and I think you did a wonderful job.
Great.
We
Thank
will
you so
be
much for having me. It was great fun.
we'll be having some tea and coffee in a moment. You'll be opening the library shortly. The library will be opening in about 10 minutes. Unfortunately, I don't think the observatories will be opening tonight. Typical Melbourne.